The A320 is a short to medium-range transport jet. The A320 family of aircraft consists of the A318, A319, A320, and the A321. Minor differences exist between the series. The aircraft requires a flight crew of 2 pilots. The required in-flight staff is determined by your airline and is shown on this frame. This frame shows the series of aircraft and the cabin configuration in your fleet. Actual layout of the cabin and operation of the doors will be described in other modules. Notice the location of the service equipment when the aircraft is at the gate. Now here we show some operating limitations of the aircraft. Notice the maximum flight altitude and the takeoff and landing weight limits. Always refer to your ECAM for up-to-date detailed information. For the remainder of this module, we'll provide an overview of the aircraft features. The AC external power receptacle is located as shown. It is equipped with a flight interphone jack that allows the ground crew to communicate with the pilots during pushback or tow. On this frame, we show the electrical system diagram as it appears when powered by external power. Notice the other available sources of AC power are the engine-driven generators and the APU generator. PDOT probes, static ports, and angle of airflow sensors are installed. A total air temperature probe is installed as well. These items provide air data and angle of attack information to the ADARU. Separate alternate static ports provide static pressure to the standby airspeed indicator and altimeter. The ADARUs provide air data and inertial reference data to the aircraft systems. Much of this information is constantly displayed on the flight instruments. The weather radar antenna is located behind the radome in the nose section of the aircraft. The antenna is a flat dish type, typical for a color radar display. This frame shows the location of various antennae on the aircraft. Control of the landing gear is provided by the landing gear lever. The landing gear normally retract and extend hydraulically, but can also extend by free fall. When the landing gear are retracted, they are completely enclosed by doors. Nose wheel steering is hydraulically operated and can be controlled by the steering hand wheel or the rudder pedals. The steering hand wheel provides a maximum steering angle of 75 degrees, while the rudder pedal steering provides a maximum steering angle of 6 degrees. Each of the main landing gear has 2 wheels. The main gear wheels have hydraulically operated brakes with anti-skid protection. Also, an auto brake system is installed and is used both for rejected takeoff and landing. Flight crew oxygen is provided by a gaseous bottle. The oxygen blowout disc is located as shown. If this disc is missing, the crew oxygen bottle requires servicing before flight. Cabin oxygen is provided by oxygen-generating canisters. Additionally, the cabin is equipped with portable oxygen bottles or POBs. The aircraft is equipped with a pressurized forward, aft, and bulk cargo compartment. The forward and aft cargo doors are normally operated with hydraulic pressure. The cargo compartments are not ventilated and will not normally support a fire. However, the compartments have smoke detection and fire extinguishing systems. Two air conditioning packs are installed to provide environmental control. On the ground, the packs can receive compressed air from a ground source, the APU, or the engines. During flight operations, the pneumatic air is normally supplied by the engines. The engine operates at Stage 3 noise levels, allowing the aircraft to meet or exceed the noise requirements that were set for the year 2000. The autothrust system is normally used to set the power in flight. Autothrust is normally engaged after takeoff by moving the thrust levers back to climb power. With autothrust active, the autothrust levers do not move, but the thrust is automatically set according to the phase of flight. At any time, the pilot can manually move the thrust levers to control the power setting manually. The engine is equipped with a thrust reverse system, which is hydraulically operated. The fan airflow provides reverse thrust, and the primary thrust continues to flow normally. Now note, the A320 does not perform power backs. The engine fire detection system detects fire conditions. Engine fire protection is controlled from the flight deck and is provided by 2 agent bottles for each engine. Wing anti-ice is applied to the 3 outboard slats of each wing. Wing anti-ice is operated in flight when required by icing conditions, but can also be operated for 30 seconds on the ground for testing purposes. Engine anti-ice is applied to the engine cowl. Engine anti-ice may be operated on the ground or in flight when required by icing conditions. Electrical anti-ice is applied to some of the flight deck windows. Electrical anti-ice is operated for all flight operations to inhibit ice buildup. Electrical anti-ice is applied to the air sensing probes. Electrical anti-ice is operated for all flight operations to inhibit ice buildup. The standard fuel system consists of 3 fuel tanks with fuel capacities shown on this frame. Fuel pressure is normally delivered to the engines and APU by the use of electrically powered boost pumps. Each wing tank directly feeds its own engine. However, either wing tank can feed any engine or the APU by opening the fuel crossfeed valve. The center tank can feed both engines and the APU. However, the APU is normally supplied fuel from the left wing tank. Pressurized refueling is accomplished at the right wing. Note the location of the fueling manifold and the refueling panel. The aircraft is equipped with 3 hydraulic systems. They are green, blue, and yellow systems. The green and yellow hydraulic systems are normally pressurized by an engine-driven pump. The power transfer unit, or PTU, can provide pressure from the green system to the yellow system or vice versa when necessary. The yellow system also has an electric motor-driven pump, which is normally used during ground operations. The blue system is normally pressurized by an electric motor-driven pump, but can also be pressurized by the ram air turbine, or RAT. The blue system can operate an emergency generator to provide electrical power when no other source of AC power is available in flight. All primary flight controls are hydraulically operated. Control is provided by 2 elevator aileron computers, or ELACs, 3 spoiler elevator computers, or SECs, and 2 flight augmentation computers, or FACs. The flight control systems operate under laws which provide different levels of automated protection against overspeed, bank, wing loading, stall, and other adverse conditions. The normal law, alternate law, and direct law operating modes are available and are described in the flight control modules. In general, the flight controls require hydraulic operation and require computer signals. We'll now provide a brief overview of all flight controls. The ailerons and elevator are normally controlled by the ELACs. Movement of these flight controls are a computerized response to a side stick or autopilot request. The rudder is normally controlled by the FACs to provide turn coordination and yaw damping. The direct rudder pedal inputs to the rudder are mechanical and require no computer operation. The secondary flight controls require hydraulic pressure to operate. These controls include the spoilers, high lift devices, and trimmable horizontal stabilizer, or THS. The spoilers are controlled by the SECs, and the SECs also provide a backup control for the elevators. Four of the spoilers automatically augment the aileron lateral commands. Spoilers 2, 3, and 4 can be extended in flight as speed brakes by use of the speed brake lever. As speed brakes, they'll destroy lift and induce drag to decelerate the aircraft or increase descent rates. Spoilers 1 to 5 operate as ground spoilers and are normally armed for automatic deployment during an RTO or during landing. The ground spoilers aid in deceleration during rejected takeoffs and landings. The ground spoilers can only extend when there is weight on the main gear. The trimmable horizontal stabilizer, or THS, is normally controlled by one of 3 electrical motors, which are signaled by the ELACs or SECs. The actual drive operation to the THS is provided by the green or yellow hydraulic system. The THS is manually moved with the green or yellow hydraulic operating system. If they both fail, the THS will not move. The slat flap control computers, or SFCCs, provide control for the hydraulically operated slats and flaps. There are 5 slat segments on the leading edge, and the trailing edge has outer and inner flaps. The flap lever on the pedestal has 5 detent positions to control the position of the slats and flaps. This frame displays the normal flap settings for takeoff and landing. The outflow valve provides control over cabin pressurization. Pressurization system operates in either the auto or manual modes. Overpressure relief and negative pressure relief are provided by the safety valves. The APU is located in the tail section of the aircraft and provides electrical power and bleed air. Inlet air for the APU combustion enters through an automatic flap on the lower side of the fuselage. APU exhaust is delivered straight out of the aft end of the aircraft. With an inoperative engine-driven generator, the aircraft can dispatch with the APU as the second source of electrical power. Certain restrictions apply and are noted in the MEL. The APU can provide electrical power to the maximum flight altitude. The APU can operate 2 packs up to 15,000, but operates only 1 pack from 15,000 to 20,000 feet. APU fire protection is provided from one agent bottle. Controls for this bottle are provided on the overhead panel and on the external APU control panel.
The aircraft is equipped with a high-level auto-flight system. Inputs to the auto-flight are made through the Flight Control Unit, FCU, or the Multifunction Control Display Units, MCDUs.
The FCU provides a means to select vertical and lateral modes and speed control. When the FCU is used to control the auto-flight, the system is said to be operating in a selected mode. The MCDUs provide a means to control the flight management system to fly an automated route. When an MCDU is used to control the auto-flight, the system is said to be operating in a managed mode. As you can imagine, we'll learn much more of the auto-flight system in this course. Well, this completes our overview of the A320 systems. You'll receive detailed information on all systems later in this course. For now, let's answer some questions on what you've learned. This module describes the A320 principal dimensions and required ground maneuvering distances. Additionally, we'll identify the location of compartments, ground servicing panels and connections, and the location of various antennas. We'll provide the A320 information as primary and also provide information for the A319 differences. Let's begin with the dimensions. The overall width of the fuselage is 3.95 meters. The cabin is designed to be wide and comfortable compared to other aircraft this size. Therefore, this cabin is described as a single-aisle cabin that is not a narrow body.
The overall length of the A320 is 37.57 meters. The height of the vertical stabilizer is 11.755 meters.
The distance from the nose to the nose gear is 5.07 meters. The nose gear is located approximately at the location of the cabin entrance door. Keep this in mind when making tight taxi turns. The distance from the nose gear to the main gear is 12.64 meters. The distance from the aircraft nose to the main gear is 17.71 meters. Take a look at the differences for the A319. The distance from the ground to the eye level of the pilots is 4.56 meters. Also, we show the distance from the ground to the bottom of the cabin doors. Okay, we've covered all the dimensions for the side view. Here they are again for your review. The wingspan is 34.1 meters, and the span of the horizontal stabilizer is 12.45 meters. The distance from the hub of one main gear to the other is 7.59 meters. The bottom of the engines is only 0.56 meters from the ground. The distance from the nose cone of one engine to the other is 11.51 meters. The ground maneuvering diagram is shown on this frame. The minimum theoretical pavement width for a 180-degree turn is listed on the chart as 22.80 meters. Now you should note that this width assumes the turn is started with the outboard main gear on the edge of the pavement and a maximum effort turn is accomplished. The maximum steering angle is 75 degrees, but the effective turn is a maximum of 70 degrees. Take a look at the differences for the A319. Become familiar with the dimensions, including the turning arc for the wing and tail, which is larger than the arc required for the aircraft nose. Take a look at the differences for the A319. This frame shows the unpressurized compartments. Starting at the front is the radome that holds the weather radar antenna. Next is the nose gear bay, then the air conditioning compartment and the main gear bay, followed last by the tail cone area which holds the APU. All other areas of the fuselage are pressurized areas. This frame shows the location of the various antennae for communications, navigation, and other guidance receivers. Some of the antenna locations may not apply to all aircraft, as certain radios, like HF, are optional. To complete this module, we show the various service panels and connection areas for ground operations. Now, many of these are for maintenance, but you should know where the panels are located so that you can check that they're closed during your pre-flight inspection. Now, let's answer some questions.
This frame shows the flight deck layout and seating arrangement. The pilot seats are electrically operated. Controls are provided for the adjustment of forward, aft, outboard, inboard, up, down, and recline with an adjustable lumbar support. There are two forward-facing foldable jump seats. One fixed jump seat on the bulkhead to the left of the cabin door, and one movable jump seat that is stowed away from the cockpit entrance while not in use. The outboard armrest of each pilot's seat is enlarged and has enhanced position controls to enable specific positioning of the armrest for use of the side stick. Note the controls for this armrest. A sliding table can be pulled out for use by the pilot. The primary flight instruments are provided on 4 display units. The primary flight display, PFD, and navigation display, ND, normally appear as shown here. While the PFD displays all primary attitude and flight information, the ND has various display modes that may be selected by the pilot. The Electronic Centralized Aircraft Monitor, ECAM, displays on the upper and lower display unit and is controlled by the ECAM control panel. The upper DU shows the Engine Warning Display, EWD, which provides a display of engine parameters and also provides abnormal and emergency checklists and warnings. The lower DU shows various system displays as selected on the ECAM control panel. To the left of the ECAM are the Standby Flight Instruments or Integrated Standby Instrument System, ISIS. To the right of the ECAM are the controls for landing gear and brakes. The glare shield holds the Master Caution Warning Lights, EPIS control panels, and the Flight Control Unit, FCU. The Master Caution Warning Lights are called attention getters, as they, along with the aural sounds, alert the crew to situations that require immediate crew awareness or immediate crew action. The EPIS control panels allow the pilot to select various display modes on the ND and to control the altimeter setting that is displayed on the PFD. The Flight Control Unit, FCU, is used to provide selected inputs to the auto flight system. The overhead panel holds system panels to control and monitor the aircraft systems. On this frame, click the hotwords to identify the system's panels. The pedestal holds various items to include the ECAM control panel and multifunction control display units, MCDUs, engine controls, communication controls, flap lever, and the speed brake lever. Click the hotwords to identify the items on the pedestal. Loudspeakers are installed in the flight deck to provide crew alerts and to hear ATC communication. We'll now describe the operating philosophy of the flight deck switches and lights. The flight deck is designed with a lights out concept. Therefore, for normal operation, the white lights in the overhead panel push-button switches should be extinguished. The illumination of a white light normally indicates the push button is not in the normal position. The illumination of the fault light indicates there is an abnormal condition. Some switches illuminate a blue light when they are selected on to advise the crew that they are selected on and operating. Additionally, a green light may be used to advise the crew of a normal operation, such as when the APU is available. Green lights indicate a normal condition. System information is provided to the crew only when there is a need to know. The need to know situation is based upon the particular phase of flight. This frame shows the phases of flight that are considered. While some indications are available in one phase of flight, you will find they are inhibited in other phases. We will discuss the flight phases as we train the particular systems. To finish this module, note the locations of emergency equipment in the flight deck. Click the hotwords as desired to identify all items on this frame. When you are ready to continue, click Next to answer some questions.
Wastewater system and toilet system. The potable water system provides fresh water to the galleys and lavatory sinks. This water is also delivered to toilets as a rinse during toilet flushing. The water is stored in a 201-liter tank that is located just behind the forward cargo compartment.
Water pressure is provided when bleed air is applied to pressurize the tank. The bleed air may be applied from the operating APU and operating engine, or when a ground source of compressed air is applied to the pneumatic system. An alternate method of pressurizing the water tank on the ground is to directly connect an air pressure source to the service panel pressure port on the water service panel. There is an electrically powered water heater for each basin. There is a manual shut-off valve for each wash basin and galley area. The valve is marked with an open and shut legend to identify the two positions of the valve. While flight crews will not normally operate these valves, it may be necessary to close a valve in the event of a leak during flight. The tank may be refilled or drained from the service panel located on the bottom of the fuselage. The water quantity indications are displayed on the service panel and on the forward attendance panel. Wastewater. The wastewater from the lavatory sinks and galley areas is drained overboard through electrically heated drain masts. The wastewater drain force is provided by cabin differential pressure when the aircraft is in flight or by gravity when the aircraft is on the ground. An air stop valve is used to inhibit the overflow of air unless the sink is intentionally drained. The forward lavatory sink and galley areas drain through the forward drain mast. The aft lavatory sink and galley areas drain through the aft drain mast. Toilet flushing. The aircraft is equipped with a single 45-gallon waste storage tank. The tank is maintained at a negative pressure in order to forcibly draw waste from the toilet when the toilet flush valve is opened. Waste tank negative pressure is provided by cabin differential air when the aircraft is above 16,000 feet. When the aircraft is below 16,000 feet, a vacuum generator provides the negative pressure. The flush sequence activates both a rinse valve and a flush valve. The valves are electrically operated. The rinse valve applies fresh water from the potable water system to the toilet bowl, and the flush valve opens to evacuate the contents of the bowl. If a flush valve fails to operate, a manual-operated flush control handle is located under the toilet bowl. A flush valve that remains open will allow cabin air to be continuously discharged overboard and produces a loud noise. Ground personnel can rinse and flush this system through a service panel under the fuselage. The waste level of the tank is displayed on the forward attendance panel. Now let's answer some questions about this system. This module describes the location and operation of the exterior lighting. The controls for the exterior lighting are located on the exterior lighting overhead panel. Notice the layout of the switches and their position on this panel. There are 3 synchronized strobe lights installed, one on each wingtip and one below the tail cone. These lights are controlled by the 3-position strobe switch. On and off positions manually turn on or off the strobe lights. The auto position will cause the strobe lights to operate automatically when the main gear strut is not compressed. Thus, auto operates the strobes when the aircraft is in flight. If the strobe lights are off in flight, the green strobe light off memo message displays on the engine warning display, or EWD. There are 2 flashing red beacon lights, one on top and one on the bottom of the fuselage. They are controlled by the 2-position beacon switch. The beacon lights are turned on before aircraft movement or before engines start. There are 2 wing lights on each side of the fuselage. The lights are turned on to illuminate the leading edge of the wing and the engine air intake when a visual inspection of icing is desired. The 2 wing lights are controlled by the 2-position wing switch. There are 2 sets of navigation lights on each wing tip and in the APU tail cone. This provides a full backup set of navigation lights to be selected by the crew when necessary. Both sets of navigation lights are controlled by the 3-position nav and logo switch. The off position turns all navigation and logo lights off. Position 1 turns on the logo lights and the first set of navigation lights, while Position 2 turns on the logo lights and the second set of navigation lights. Logo lights are installed in the upper surface of each horizontal stabilizer to illuminate the logo on the vertical stabilizer. The logo lights are controlled by the nav and logo switch in addition to some automatic sensors. Logo lights can operate only when the main gear strut is compressed or when the slats are extended. Thus, logo lights only operate on the ground or after takeoff and before landing. The taxi and takeoff lights are installed on the nose landing gear as shown. They are normally controlled by the 3-position nose switch and can be turned on only when the landing gear is extended. The off position turns off both the taxi and takeoff lights. The taxi position turns on only the taxi light. The takeoff position turns on both the taxi and takeoff lights. Note, the taxi and takeoff lights automatically extinguish when the landing gear is retracted, regardless of the switch position. The turn-off lights are located just below the taxi and takeoff lights on the nose landing gear. The turn-off lights are normally controlled by the two-position runway turn-off switch. The on position turns on both lights when the landing gear is extended, and the off position turns them off. Just like the taxi and takeoff lights, the turn-off lights will automatically extinguish when the landing gear is retracted, regardless of the switch position. There is one retractable landing light located under each wing. There is a three-position control switch for each landing light. The retract position is selected to turn off and retract the associated landing light. The on position extends the associated landing light. The light illuminates when fully extended. The off position turns off the associated landing light, but leaves the light assembly extended. When the landing lights are extended, the green landing light memo message displays on the EWD. Let's answer those questions. This module identifies the flight deck lighting and associated controls. The switches and knobs on the integral light panel from left to right. On the left side of the integral light panel is the variable intensity control knob for the overhead integral light. To the right of the overhead integral light switch is the ICE indicator and standby compass light switch. Next is the three-position control switch for both dome lights. On the flight deck ceiling, two dome lights are installed to provide shadow-free flood lighting. When on battery power, only the right-hand dome light can operate. To the right of the dome light switch is the switch for the annunciator lights. This switch allows the crew to select the annunciator lights to dim, bright, or test. When the switch is moved to test, all flight deck annunciator lights illuminate. A display of 8s appears in all liquid crystal displays, LCDs. All flags are displayed on the Electronic Instrument System, EIS, and standby instruments, and the cruise page will appear on the system display, SD. Further aft on the overhead panel, we find the flood light for the pedestal. This light is controlled by the floodlight pedestal knob on the right side of the pedestal. Floodlights for the main panel and integral lights for the main panel and pedestal are controlled by the floodlight main panel and integral light main panel and pedestal knobs on a panel on the left side of the pedestal. On each side of the aft overhead panel, there is a reading light knob for the pilot's reading lights. Outboard of each pilot's seat on the pillar of the lateral window, there is another reading light. The reading light has an on-off switch and a brightness knob installed on the light housing. There are two knobs located just under the Flight Control Unit, FCU. The knob on the left controls the intensity of the integral lighting on the glare shield and also the intensity of the LEDs on the FCU. The knob on the right controls the brightness of the FCU displays. There is a light under each side of the glare shield that illuminates the sliding table and map holder. The knob that controls the brightness of this light is located just outboard the light itself. Console floor lighting is controlled by a 3-position switch on each pilot's instrument panel. Let's answer those questions. The Electronic Centralized Aircraft Monitor, ECAM, provides a display of engine and system parameters and also provides various levels of alerts and memos to the flight crew. The ECAM components used by the flight crew consist of an upper and lower display unit and the ECAM control panel. The upper ECAM display is referred to as the Engine Warning Display, or EWD. The lower ECAM display is referred to as the Systems Display, or SD. The EWD is divided into 4 parts, 2 on the top and 2 on the bottom. The left part of the top section displays the primary engine parameters. The right part of the top section displays the current thrust mode, fuel indications, and the position of the slats and flaps. The bottom sections of the EWD display various messages throughout the flight. These messages are generated by the Flight Warning System, FWS, that include warnings or cautions when a failure occurs, memos for normal operations, special lines for special conditions, and advisories for advisory information. The left part can display primary or independent failures, memos, or config memos. The right part can display the special lines, left part overflow summary, secondary failures, and memos. As soon as the FWS detects a failure, and if the flight phase is not inhibited, the EWD displays the title of the failure and the actions to be taken. In most cases, the blue action line is automatically cleared when the crew performs the action. The FWS divides its functions according to these 10 flight phases. Electrical power on, first engine started, first engine at takeoff power, 80 knots, liftoff, 1,500 feet or 2 minutes after liftoff, 800 feet on descent, touchdown, 80 knots, second engine shut down, and 5 minutes after shutdown. The FWS is designed to not display certain alerts during some phases of flight. This is to ensure that non-critical items do not become distracting during high workload periods, such as during takeoff or landing. When the takeoff and landing inhibits are in effect, you will see magenta memos on the right side. These appear as takeoff inhibit during phases 3, 4, and 5, or landing inhibit during phases 7 and 8. Other specific inhibits are in effect during certain phases according to each aircraft system. At the end of each section of each chapter of the FCOM, a list of the related systems, warnings, and cautions is provided, along with a list of the phases when they are inhibited. There are 2 conditions for a failure to occur as it relates to ECAM inhibit. 1. A failure can occur before an inhibited phase and continue into and through that phase. 2. A failure can occur during an inhibited phase and continue after that phase. If a failure occurs prior to an inhibited phase, shown here as phase 3, the EWD displays the warning immediately and will also continue to display it during the inhibited phase and until it is corrected or the crew has cleared it from ECAM. If a failure occurs during an inhibited phase, the EWD will not display the warning until the aircraft enters the phase where the warning is not inhibited, shown here as phase 6. After the warning is displayed, it remains until it is corrected or the crew has cleared it from ECAM. ECAM color conventions indicate the importance of the failure or indication. In general, red indicates a configuration or failure that requires immediate action. Amber indicates that the crew should be aware of the configuration or failure but needs not take immediate action. Green indicates an item that is operating normally. White is used for titles and remarks that guide the crew to execute various procedures. Blue is used to display actions to be carried out by the crew or limitations. Magenta indicates messages that apply to particular pieces of equipment or situations, like the aforementioned inhibition messages. There are 3 priority levels for warnings and cautions that are detected by the flight warning system. These levels determine the priority of appearance on the EWD and are labeled levels 1, 2, and 3. A level 3 warning has priority over a level 2 caution, which has priority over a level 1 caution, and will appear in that order if occurring simultaneously. Additionally, there is a hierarchy of priority within the level 3 warnings. Oral warnings also have a hierarchy of priorities. Synthetic voice has priority over all other oral warnings. Oral warnings temporarily interrupt kettle, buzzer, etc., plus or minus 1 second. Single chimes are limited to 1 every 2 seconds. A level 1 caution is the lowest priority and has no oral alert or master caution. It appears as an amber caution on the EWD without displaying a system page on the SD. This level requires crew monitoring only and indicates a loss of redundancy or system degradation. A level 2 caution is the next priority and is normally accompanied by a single chime. The master caution lights illuminate steady, an amber caution appears on the EWD, and the associated system page appears on the SD. This level requires the crew to be aware of the configuration or failure, but may not necessarily require immediate action. A level 3 warning is the highest priority warning, and it is normally accompanied by a repetitive chime, CRC, or a specific oral alert. Additionally, the level 3 warnings cause the master warning light to flash, a red warning appears on the EWD, and the associated system page appears on the SD. This level requires immediate action by the crew, as the aircraft is either in a dangerous flight condition or has a system failure that affects flight safety. There are 3 types of ECAM failures: independent, primary, and secondary. An independent failure affects a component of a system that causes the component to fail or operate at a degraded level without affecting other components or systems. An independent failure appears in amber on the left memo page on the same line as the item title of the system. A primary failure affects a system or a component of a system that causes other components or systems to fail or operate at a degraded level. A primary failure appears on the left memo page in red or amber on the same line as the item title of the system and has a box around the failure. Secondary failures are the loss of a system or a degraded level of operation of a component in that system that is a result of a primary failure. A secondary failure appears on the right memo page in amber, preceded by an asterisk, and lists only the systems affected and not the component. Usually more than one secondary failure is caused by a single primary failure. Shown here is an example of an advisory. Advisories are provided when systems parameters should be monitored. An advisory is indicated by an automatic display of the related system page on the SD, with the item title pulsing normal white to bright white, and the affected parameter pulsing green to bright green. Shown here is an example of a memo. Memos are green for temporary normal operations, but can be amber for abnormal conditions. During normal cruise, there should be no memos. The takeoff and landing memos display the key items for takeoff and landing. The takeoff memo appears 2 minutes after engine start or when the takeoff config push button is pressed, provided at least one engine is running. Each takeoff memo item is displayed in green with the action item in cyan until the correct configuration for that item is selected, and when the correct configuration is selected, the action item appears green. The takeoff config line is the last line of the takeoff memo. The takeoff config test cyan will change to takeoff config normal green when a configuration test is performed if the correct responses for all items are set for takeoff green. If the configuration of an item on the list subsequently becomes abnormal, both the takeoff config and item green response indications will revert to cyan. The function of the takeoff memo is only to ensure that the listed items are properly set for a normal takeoff. It does not ensure a safe takeoff configuration for the aircraft. However, the function of the takeoff config test is to ensure that the aircraft is safely configured for takeoff. None of the items on the takeoff memo will cause a config warning if incorrectly set, except the flaps configuration. If the flaps are positioned at a position other than takeoff 1, 2, or 3, the response will be a cyan blue response, and a config warning will sound if the takeoff config push button is pressed. The takeoff config test simulates takeoff power and checks a number of parameters. See examples above. The takeoff memo remains in view until takeoff power is applied. The landing memo appears during approach at 2,000 feet AGL. It will not appear until 750 feet AGL if 2,000 feet AGL is not exceeded after takeoff, such as during an immediate return. The landing memo flaps full action item will display as flaps config 3 if the aircraft flight controls are operating in alternate or direct law modes, or if the GPWS landing flap 3 push button is on. This completes our discussion of the takeoff and landing memos. System display and status. The system display and status appear on the lower ECAM. There are 11 system display pages available, and certain pages appear automatically depending on the phase of flight. The system display page can be automatically called up as a result of an abnormal condition. Regardless of which page is displayed, the crew can manually select a system display at any time by pressing a push button on the ECAM control panel. On the bottom of the SD, there are permanent display items as shown here. They are the TAT, SAT, UTC, and gross weight. Additionally, if the G-load is less than 0.7 or greater than plus 1.4, the G-load will be displayed. We'll now sequence through a normal flight and describe the normal systems pages that automatically appear according to this diagram. This diagram shows the 10 phases of flight. For example, when electrical power is applied to the aircraft, electrical power phase 1, the doors page is displayed to allow the crew to monitor the aircraft doors and the flight crew oxygen system. When the APU master switch is selected on, the APU page appears and remains displayed until 10 seconds after the APU RPM has been above 95% for 10 seconds, or until the master switch is selected off. When the APU page blanks, the doors page will reappear. When the pilot initiates the engine start, the engine page appears. It remains displayed until 10 seconds after the end of the start sequence, when the engine mode selector is set to norm. After start, when the engine displays blanks, the wheel page automatically appears to allow the crew to monitor these items during taxi. When either pilot moves the side stick more than 3 degrees in pitch or roll, or when rudder pedal deflection is more than 22 degrees, the flight control page temporarily replaces the wheel page. This automatic display change allows viewing of the flight control page for the flight control test, and the wheel page then reappears after 20 seconds. When the first engine reaches takeoff power, the engine page is displayed. If there are no ECAM failures, it remains displayed until climbing through 1,500 feet, when it is replaced by the cruise page. The cruise page shows a combination of engine, air, vibe, and cab pressurization items to make it easy for the crew to monitor these items during the flight. The cruise page is displayed until the landing gear is extended, at which time it is replaced by the wheel page. Normally, the APU is started after landing, and the APU page displays until the APU start cycle is completed. Then the wheel page reappears. The wheel page displays until it is replaced by the door page when the last engine is shut down. The pilot can manually select any other page by pressing a SD push button. When a SD is called up that is not the normal system page for the phase of flight, the selected SD push button light illuminates. This light is a reminder that a page has been manually selected. To return to the normal page for the phase of flight, in this case doors, the pilot can press the illuminated push button or press a clear push button. Regardless of the system displayed at any time, an automatic call-up of an SD page occurs when a fault or malfunction triggers a caution or warning message. At the same time, the appropriate warning or caution message appears. If appropriate, an oral alert sounds and the master warning or caution lights come on. Additionally, the clear push buttons illuminate and a local light on a system panel may illuminate. After completing each procedure, the crew will push the clear push button until all actions and procedures are completed. At this time, the memo displays return to normal. The phase of flight page is displayed, and the clear push button light goes out. A system page may also display automatically when an advisory appears because a parameter is out of range. In this case, the parameter will pulse in green while it is outside limits. Additionally, the SD title will display flashing intensity from normal to bright. Advisories are inhibited during some phases of flight. Status page. The status page displays an operational summary of the aircraft status after the engine warning display has displayed a failure and the crew has completed all pages associated with that failure. Assume this display is the last in a series of pages for a failure. Push the clear push button one more time and the status page will automatically appear. The status page displays the messages of the effects of an FWS detected fault or reduced capability. Limitations are in cyan. Approach procedures in white, red, or amber. Corrections to apply for landing in cyan. Other information in green. Canceled cautions in white. INOPSIS in amber. And the Class 2 maintenance items in white. If more messages are applicable than can be displayed, the overflow arrow appears and the crew can view those messages by pressing a clear key. The status page also appears automatically during flight when the flat panel is positioned at 1 if the status page holds messages other than canceled caution or the maintenance part. In this case, the engine warning display screen displays the boxed STS reminder. If the status page holds Class 2 messages in the maintenance part after engine shutdown, the STS reminder flashes on the engine warning display screen. The screen displays the maintenance part only when on the ground before engine start or after engine shutdown, phases 1 and 10. We will now show the sequence of displays that appear when the blue hydraulic reservoir overheats. We begin with the normal display. The aircraft is climbing with the center tank feeding and the wing anti-ice is on. Notice the cruise system page is displayed and notice other normal parameters. ECAM automatically calls up the hydraulic systems page to display a synoptic of the hydraulic system. Notice that overheat is displayed in amber for the blue system. The action on the engine warning display instructs the crew to turn off the blue electric pump. The crew has selected the blue electric pump off and the blue system now has low pressure. When the blue hydraulic system loses pressure when the pump is turned off, hydraulic blue sys low press appears as a primary failure. The master caution lights remain on, as does the push-button fault light on the overhead panel. On the right side of the engine warning display, you see the secondary failure result is a loss of some flight control items. The clear push button remains lighted, so one of the crew will push it. When the clear push button has been pushed, the hydraulic messages disappear from the engine warning display, and the flight control systems page. The flight control surface actuators that are depressurized as a result of our action are shown in amber. The clear push button is still lighted, and the overhead light is still on. The clear push button remains lighted, so one of the crew will push it. When the clear push button has been pushed, the hydraulic messages disappear from the engine warning display, and the flight control systems page is displayed. The flight control surface actuators that are depressurized as a result of our action are shown in amber. The clear push button is still lighted, and the overhead light is still on, so one of the crew will push it. The memo area on the engine warning display returns to normal and the status page appears on the SD to display the procedures for completing the flight with the faulty blue hydraulic system. The clear and STS push buttons are now lighted, so one of the crew pushes the clear button a third time. The clear push button light now goes off, the appropriate SD page is displayed, in this case cruise, and the STS reminder appears on the engine warning display to remind the crew of the available status page information. The overhead light remains on until the condition is corrected. This sequence has provided an example of the ECAM operation during an abnormal condition. DU failures. If the upper DU fails or is switched off, the engine warning display has priority and automatically moves down to the lower DU. During the single display operation, if the flight crew desires to display the SD or status pages, the desired SD or status page push button can be selected to temporarily display it on the lower DU for a maximum of 3 minutes. When the push button is released, the engine warning display is again displayed. We're now back to normal when a failure of the lower DU occurs or the lower DU is switched off. As before, the crew can push and hold the desired systems page push button to temporarily display the SD or status page on the upper DU for a maximum of 3 minutes. When the push button is released, the engine warning display is displayed. Another way to display the SD or status pages when the lower DU has failed or is off is to select the ECAM ND transfer switch on the switching panel to display it on the NDU. We're now back to normal when a failure of both DUs occurs. The crew can use the ECAM ND transfer on the switching panel to display the engine warning display on a navigation display, and if necessary, can push and hold a system page push button to temporarily display the system status page on an ND for a maximum of 3 minutes. Let's answer those questions. The emergency lighting system provides lighting for an emergency evacuation. Lights controlled by the emergency exit light selector in the cockpit or by the emergency push button on the purser panel are provided in 3 basic groups: exit signs, aisle escape path lights, and overhead lighting.
Electrical power for these emergency lights is provided either by the DC shed essential bus or by internal batteries in the light assemblies. The expected time of operation from battery power is 12 minutes.
The emergency exit light selector is a 3-position switch with on, arm, and off positions. When the selector is not in the on position, and the emergency push button at the forward attendance panel has not been pressed, the DC shed essential bus will charge the internal batteries. The on and off positions are used to manually control the lights. When the switch is in off, the emergency exit light off light illuminates amber. The arm position is normal for flight operations. With the selector in the arm position, the aisle escape path lights and exit lights come on if normal electrical power has failed or the DC shed essential bus fails. The overhead emergency lights will come on for the same conditions and will also come on if only AC bus 1 fails. Pressing the emergency push button on the forward attendant panel will cause all of these lights to come on. The emergency lighting system also provides lavatory auxiliary lights that are constantly illuminated and are powered by the 28-volt DC essential bus. The overwing escape route lighting and escape slide lighting illuminates when the door slide is armed and the door or emergency exit is opened. These lights are supplied by internal batteries. The A320 has 4 cabin doors. The left forward door is normally used by passengers and the other doors are for aircraft service. All 4 doors can be used as emergency exits and are equipped with inflatable escape slides. Overwing emergency exits are located on each side of the aircraft. There is one overwing escape slide on each side. The overwing escape slide is stowed inside a compartment in the fuselage close to the wing root. There is one overwing exit on each side of the A319. There are 2 overwing exits on each side of the A320. The operation of the overwing exits is the same for all aircraft. The A319s have 2 cargo compartments and 2 cargo doors, forward and aft. The A320s have 3 cargo compartments and 3 cargo doors, forward, aft, and bulk. The bulk and aft compartments are 2 portions of the same area, but each portion has a separate door. All cargo doors are located on the right side of the aircraft. There are 4 small doors in the bottom of the fuselage close to the aircraft nose that provide access to the avionics compartment. The status of the aircraft doors is shown on the ECAM door oxygen page. This page is the default system's display when the aircraft is parked. A generic symbol for each door and escape slide is displayed. A door that is not closed and locked displays in amber and is labeled. A door that is closed and locked displays in green with no label. There is a sliding window on each side of the flight deck that can be used for emergency exit. Escape ropes, normally stowed in compartments after the window, can be tossed out of the window and used to lower oneself to the ground during emergency exit. Ensure the rope is firmly attached before you exit through the window. On this frame, you can click all doors and watch the symbols indicate their open or closed status. The overwing escapes are equipped with slides. The slides are always armed unless disarmed by maintenance. Therefore, a white label normally appears beside the associated door. Each cabin door is equipped with a slide that must be armed after the door is closed and locked. This frame shows all doors closed and locked, but none of the door slides are armed. When a door slide is armed, a white label appears beside the associated door. All slides are now armed. Okay, we finished with the description of the door indications. Now, let's learn how to operate the doors. Before we describe the door operation, notice the height of these doors from the ground. Assist handles are located close to the door frame, and there is also an assist handle on the door. Hold on to the appropriate handle when operating a door to protect yourself from a wind gust or other condition that could pull you off balance. The 4 cabin doors are manually operated and are locked and unlocked by use of a control handle. An indicator displays the locked or unlocked condition of the door. The doors can be opened in the normal, disarm, or emergency armed mode. Opening the door in the normal mode will not cause the slide to deploy, but opening the door in the emergency mode will cause the slide to automatically deploy and inflate. To close the door, the gust lock on top of the support arm must be pressed to unlock the door from the open position. Swing the door until it is closed, then move the control lever to lock the door. The control lever arms the slide, and a small window displays the arming status of the slide. The slide must be disarmed before the door is opened, so as not to activate the emergency mode. Each door has an observation window equipped with a sun shield. Near the window there are 2 electrical indicators which can be viewed through the window or from outside. One indicator illuminates white when the slide is armed and the door handle is moved up. One indicator flashes red if the cabin remains pressurized, when both engines are off and the door is disarmed. A door is normally opened by moving the control lever to disarm the slide and unlock the door. The door is then moved full open until the gust lock is engaged. Before we leave this frame, notice the door support arm holds the emergency opening cylinder and the slide pressure gauge. We'll now describe opening the door in the emergency mode. When the door is opened with the slide armed, the door emergency opening cylinder provides the pressure for fast opening of the door. With the slide armed, the slide will deploy and inflate automatically when the cabin door is opened. In the event that the escape slide does not automatically inflate, a red manual inflation handle can be pulled. Each slide is equipped with emergency lights that automatically illuminate when the slide is deployed. The lights are electrically powered by a battery in the slide pack itself. The cabin doors can also be closed and opened from the outside. However, the arming of the slide can only be performed from inside. This completes our description of the operation of the cabin doors. The overwing emergency exits can be opened from outside and inside. Inside opening instructions are placarded on the exit frame and on the passenger seatbacks. A cover flap protects the control handle. A slide armed indication illuminates white, and a handle light comes on when the cover flap is removed. Overwing slides are stowed in a stowage compartment on either side of the fuselage. This respective overwing escape slide is automatically deployed when an overwing emergency exit is opened. 2 emergency lights underneath the wing exits illuminate the escape way leading to the escape slide. If the automatic sequence fails, a red handle in each exit frame can be pulled to manually inflate the slide. The forward and aft cargo compartments are capable of holding containerized cargo. The doors on the forward and aft compartment open outward and upward. They are operated with yellow hydraulic system pressure. The doors are manually locked and unlocked, but hydraulic pressure is required to open or close them. The yellow system electric pump normally provides the pressure, but a hand pump is installed at the hydraulic maintenance panel when the electric pump is not operative. Note, when the electric pump is operating the forward or aft cargo doors, the only other yellow system items that can operate are the braking and engine 2 reverse. The bulk compartment door is manually operated and can be opened from inside or outside. It is a plug-type door that opens inward and upward. This frame shows the ECAM door oxygen page display for the LCD type and for the CRT type. These pages have similar displays, but our pop-up shows the differences. This completes our description of door operation and indications. Now let's answer some questions.